kick this off. And let's get back to the beginning. And let's present. Present. Alrighty, so this is just a quick overview of OpenTelemetry. And if we're going to talk about OpenTelemetry, we have to talk about the problem that it's solving. And that problem is distributed transactions. And the part of solving distributed transactions that OpenTelemetry solves is telemetry. So telemetry is the process of collecting information about objects that are far away and sending that information somewhere electronically so that it can be analyzed. The world of observability is big and it has a lot of moving parts. The part that OpenTelemetry solves is standardizing the data that systems generate so that we have a standard common language for describing systems. And that allows analysis tools to really get a much better sense of what systems actually are. And it creates for a sort of greenfield of possibility to build new analysis systems all on top of the same data. But the reason why we need this is because transactions are becoming more and more distributed. So what do I mean by a distributed transaction? Let me walk you through a super basic example. This is like the world's simplest app. Let's say we've got a system where you have a client, and that client is a mobile client that wants to upload a photo and a caption for that photo and send it over to the server to get stored. Now, of course, we know it's never this simple, right? Like that server is actually a bunch of systems. It's probably a reverse proxy that sits and then talks to an authentication system. And then that proxy will write that image down to scratch disk and then send that image and the caption to an app, which will then upload the image into cloud storage like S3, and then send the URL and the caption over to a data service. And that data service will sit in front of a couple other cloud databases, like let's see, it sits in front of a Redis for caching that information and then stores it permanently in SQL. So you can see right here, this is like a really simple application, but it's already fairly distributed. There are a lot of moving parts. There are a lot of separate services. And as we move into a serverless world, this becomes even more distributed. So microservices, serverless, growth in scale, growth in diversity means that our systems become really, really complicated. It's not just one big monolith. Now it's many different systems talking to each other. And that means when you're trying to reconstruct a chain of events to actually figure out where the error that the user saw came from, or why the page was slow when it loaded, that's becoming harder and harder to do the more distributed our systems are becoming. So for example, logging. All of these systems produce logs. We're all used to looking at log data. But if you try to reconstruct one of these big distributed transactions out of your logging system, it becomes really difficult to do because you have to find and filter to just get the logs that were in your particular transaction. And if you had something like a transaction ID, or as we'll call in a moment, a trace ID attached to all of these logs, then you'd be able to do a query, which is find all the other logs that are in this transaction. But with a traditional logging tool, you don't have that because you don't have that kind of context. Likewise, we have metrics and dashboards. We're really used to looking at those. But it can be difficult to connect what you're seeing in those aggregates, in those dashboards, with the actual events that are being produced. And that's because those systems tend to be completely separate. We have one system, like a logging system for storing events, and then we have another metric system that's showing you metrics, but the two systems aren't tied together. And even at a fundamental level, the data isn't tied together. And so that just makes the amount of time you have to spend connecting the dots difficult. And it makes it really difficult to automate the connecting of those dots. So this is where OpenTelemetry comes in. What OpenTelemetry does is it unifies all of these different signals into a single system, with tracing, distributed tracing being the fundamental backbone that metrics and logging sit on top of. And by combining that into a single data stream and correlating data across these different streams, we're creating a much more rich set of data that's allowing us to build new tools and new technology that provide more insight and are going to be able to automate a lot of the work that you have to do today. So because people are not familiar with distributed tracing, I do just want to give a quick overview of distributed tracing and how it works, because this is sort of the fundamental you get with OpenTelemetry. So just imagine real quick, you have two servers, server A and server B, and you have a sequence of operations and server A talking to server B over network call. So distributed tracing at its fundamental is about having some amount of context that follows the flow of execution. And when that flow of execution hits a network call, that context then gets propagated. So we call this context propagation. So within each process, you're following along. So in the background, at any moment, you can call up this context object and ask it for a trace ID or an operation ID or any piece of baggage you want to add to it. And then when you hit a network call, you inject that context, say as HTTP headers. And then on the other side, the tracing system extracts that call and then turns it back into a context object, which continues along. And so this gives us the ability to trace the entire distributed transaction, no matter how many services are involved in it. So when you get all of your data in tracing, you can then form a graph. So you'll see these kinds of graphs if you start looking at tracing systems. They're pretty common, but just to explain how they work, each color-coded line here represents an operation, possibly on a different server. The length of the line represents the latency or how long that operation took, and the arrows represent network calls. So this is sort of our original simple app. We have a client and it's talking to a reverse proxy, an authentication server, and so on and so forth. Being able to connect all of this together automatically into a graph is really powerful. For one, you can visualize things like latency. You can see where the time is going in your system. That's something that can be somewhat difficult to do if you're just looking at logs. You can also quickly identify what service the error is coming from, which is also really important because you might see an error downstream, say in your client reporting a 500 error, but you want to quickly trace that back to the service that actually generated the error. And that's much easier to do with a tracing tool. And then, of course, you want to have fine-grained events. This is basically logging, only now your logs are contextualized by the trace, which means if you find one log, you can find all the other logs in your transaction. And that's a really powerful time-saving tool. And last but not least, you want to be able to connect these transactions together in aggregate with other transactions so that you can create dashboards and metrics and things of that nature. So you want to be able to correlate these. And we're able to do that by attaching attributes to each one of these operations. So what host it was on, if it was a client request, was it a 500 error, et cetera, so that you can then build graphs out of this information. So that's like the basic of what OpenTelemetry provides. Let me just check the time real quick. Cool, I got a couple more minutes. I want to just pivot to how OpenTelemetry is actually structured because we're going to be installing the system on Lambda. It's good to know just what the actual pieces are. So OpenTelemetry is divided into a couple of pieces. One piece that you would install in your client, so this green circle is a client, is what we call the SDK. This is the OpenTelemetry implementation that actually collects the data. You install all your plugins into this, your exporters, all of that stuff happens at the SDK. However, the SDK is not what you use to instrument your system. The SDK can get installed by the application owner, or in the case of Lambda, maybe even a third party. And then when you go to instrument your system, you use the API. One advantage of having the API separate from the SDK is that it comes with no dependencies. So the API is just the interfaces that you use to instrument your system. And that allows you to separate out what implementation you're using from the instrumentation you're providing. This is especially useful for shared open source libraries like frameworks and network clients and things like that, where that library is going to be installed in a lot of different applications. And when that library gets installed in all these applications, it doesn't want to haul in some huge dependency chain that might create conflicts. So when you instrument your app or your library, you just use the API. And we'll see why this is helpful in Lambda in a minute. So again, this is just to kind of show how that works. So you have your frameworks, your HTTP clients, your SQL clients, your app code, that all talks to the API. And then the API then forwards that information on to the SDK implementation. So long-term, we hope that these instrumentation calls can actually be moved natively into frameworks and clients so that out of the box, your web framework will actually have observability installed, and the people developing that web framework will be thinking about not just testing it, but how you would want to observe that system in production. So we're hoping to bring observability more to the forefront of people's minds by giving them a tool that they can actually install successfully directly into their libraries. The other important piece of OpenTelemetry is what we call the collector. So the collector is a separate service that the SDK talks to. So you tend to leave the SDK in a default mode, speaking OTLP, which is the native protocol for OpenTelemetry, and then move all of your configuration to the collector. So the collector is where you do data processing. That's where you can tee it off to talk to multiple systems in multiple different languages. For example, you might send your traces to a Zipkin backend and your metrics to a Prometheus backend. All of that processing and configuration you want to do in the collector. You can do this directly in the SDK using exporters, but if you do it in a collector, then you're able to redeploy and change your observability topology without having to redeploy your application. So by pulling this out from your application, this helps operators be more in control of their actual observability pipeline. Now, I should mention OpenTelemetry doesn't come with an analysis backend. That part is, as we say, sold separately. And that's because OpenTelemetry is a standardization process. So we want to standardize how this data is produced, collected, and sent off to different analysis tools. But the analysis tools are where all of the innovation is happening. There's no standard way to look at this data. Instead, we want to have competition there, and we want to invent new and more interesting and more helpful ways to look at this data. So OpenTelemetry tries to be vendor neutral and become an industry standard. And in fact, all of the major players in the observability industry are involved in OpenTelemetry at this point. Last but not least, the actual process for developing all of this, if you want to get involved in OpenTelemetry, is through a specification process. So we have a specification where we all come together and work on the design of that system. Then we cut a release of that specification, which then gets implemented by the maintainers of the different language implementations. And in fact, just this week, we've cut a 1.0 release of the specification. So release candidates and 1.0 implementations are about to hit starting next week. Okay, so that's a very quick, very fast-paced overview of OpenTelemetry and how it works. Now I'm going to hand it off to Nizar to talk about Lambda specifically.
Thank you, Ted. So let me share my screen. Ted, you might want to, I think you'll have to stop.
Oh yeah,
sharing your
screen. I gotta do here. Let me see. Stop share. Oh, I was still sharing. Try it now.
Okay. Then let me do this one. Cool. All right. You can see my slides?
Yeah, we can see them.
Cool. Thank you, Ted. So in this part of the session, we will dive deep into the AWS distribution for OpenTelemetry, specifically understanding why AWS is investing in OpenTelemetry, why are we creating a distribution out of it, and then focus our kind of conversation more towards what we have done for the Lambda use case, right? So customers we know are running applications in different compute containers, EKS, ECS, on-prem, EC2, as well as Lambda. And each environment is a little bit different, and it works different in terms of their architecture and the communication patterns. And Lambda is also different. So we want to focus this conversation into Lambda, what we have done specifically to make OpenTelemetry integrated very well with Lambda, and how we can use OpenTelemetry SDKs, APIs, and collectors and agents that Ted just showed for instrumenting your Lambda applications. So to get started with, like at a very high level, like why AWS Distro for OpenTelemetry? So we have heard from our customers, many of them are using multiple frameworks, SDKs, and agents to collect logs, metrics, and traces, right? And this is more towards aligning with their use cases, or more towards what tools they have been using in the past, and they want to continue doing that, and more towards what each team is comfortable in using and have invested heavily into that. There are a couple of problems with this, right? So with multiple tools, the data is now distributed into multiple different backend monitoring services to different set of agents and SDKs. That adds a lot of investment of time and resources into making it work at the production capacity. So to managing it, maintaining those agents, upgrading it, patching it, getting new versions, and so on. Not only that, the data that comes out of these SDKs and agents is now disconnected. There's no correlation between the value that we want to add between metrics, logs, and traces, something that Ted already kind of spoke about, right? The value is understanding this correlation between why is there a peak in the error rate aligned to which services it's impacting and how it's impacting my end users. So in order to solve the problem, OpenTelemetry comes in the picture. It provides a standardized set of APIs, SDKs, and agents to collect your metrics and traces and send to multiple destinations at once. So just with a simple configuration change, you can say, I want to send my traces to AWS and Lightstep, and I want to send my metrics to a Prometheus backend or any other vendor-specific backend. The other benefit that it provides is it provides this correlation context, right? So there is the data that is being generated, metrics and traces, has a correlation context which helps you connect the dots in your monitoring service. And this correlation context is done at the ingestion of the data. So the implementation of the monitoring backends to create innovations around it, or create machine learning models, or create more dive deep triaging workflows becomes very simple for the monitoring backends. So AWS Distro for OpenTelemetry is a secure, production-ready, open source distribution of the upstream OpenTelemetry project. We are upstream first. That means we invest in all our 100% of our code goes to the upstream OpenTelemetry repo. We then create a distribution out of it. We run through a lot of security analysis, security checks, pen tests, performance tests to make it ready for a production use in AWS. And we also back it with AWS support. The other thing we have done is we have tight integration with AWS services. And one of the services we'll show in case of Lambda today in the demo. We also integrate with container services. So, or we are in the process of integrating and improving that. So when you're creating a Fargate task, or you are creating a cluster, automatically you can select that I want to collect my traces and metrics, and here are all my destinations I want to send my data. And automatically we will provision for it, we will deploy it, we will configure it, and so on. At the same time, this AWS distro has exporters for not only AWS services, but also for partner-specific services as well. So you can send traces to X-Ray, metrics to managed Prometheus service and CloudWatch, and also you can send trace data to partner solutions like Lightstep is one of the examples, and we'll show that in the demo as well. So where are we currently with the Lambda support for OpenTelemetry, and where are we going next? So currently we support Lambda in Python through the AWS distro for OpenTelemetry. It is based on the Lambda extensions. We will have a Lambda layer, or we have a Lambda layer that you can add to your functions. And we a couple of areas that we have invested in to make it very simple to use. So we have invested in auto instrumentation in Python. So a lot of your calls and your dependency calls that you're making or AWS calls that you're making is automatically instrumented. And that's what we will show in the demo, that if you're making a call to S3 or DynamoDB through Lambda, automatically we instrument the call so that you don't have to write any custom instrumentation code. The other investment we have done is automatically we collect resource-specific information. So we collect Lambda function name, Lambda function version, its on. So it helps in the end when you're building a monitoring experience or a triaging experience, it helps to connect the application performance data to more of an infrastructure or resource performance data to tell a better story. At the same time, we have enhanced kind of worked on using the Lambda extensions and layer technology to provide a batching across within the invoke, and we aim to expand on that to have batching across invokes eventually in future. And today we support sending traces to X-ray and OTLP protocol. So any of the partner solutions like Lightstep, which uses OTLP protocol, you can send the data to them as well. Okay, so let's in the next few slides, let's dive a little bit deep into how the OpenTelemetry integration has been set up within the Lambda premises or the Lambda architecture, and how the calls are being passed from the point that you invoke a function to the point that the call is made to the Lambda service, to the point it goes to the runtime, and then to the point where it goes to the OpenTelemetry SDK and the collector, which is then batching the data and sending to the backend service. So this is kind of the, as I mentioned, like the entire Lambda integration is based on, for OpenTelemetry, is based on its the Lambda extensions that came out last year. So I want to kind of dive a little bit deep into kind of explaining how the calls are going with that. So before the Lambda extensions, here was the life cycle of the Lambda, right? You initialize the function, then you execute the function, and you end the function. However, with the advent of the Lambda extensions, there is more control. There is more kind of specific communication that you can control and you can handle. So it's divided into three phases. One is the initialization phase, one is your function invoke phase, and then one is your function shutdown phase. So in the initialization phase, there is extensions. Extensions is basically a way to bring your own agent or bring your own code that runs alongside your function, and you can control the lifecycle of that. So let's take a look into each of these initialization, invoke, and shutdown phase and see how the communication happens with the Lambda extension. So in the initialization phase, if we take a look at it, there are three different kind of areas in the entire Lambda execution. There is the Lambda platform service, there is the Lambda runtime, and then there is the Lambda extensions. And when there is this Lambda extensions is where OpenTelemetry fits in. So we have created a Lambda extension specific to OpenTelemetry where the collector runs as part of your function execution. So when an extension is initialized, all the extensions need to be initialized before your function or the runtime. And they have to register with the platform so that the platform knows that, okay, I have this extension, which is the OpenTelemetry extension. I am initialized and I'm ready to take request. And then once all the extensions have been initialized, you can have multiple extensions, right? So you can have OpenTelemetry extension, you can have another extension for another of your observability solution, or you can have your own custom extension that you're doing as part of your Lambda execution. Once all the extensions are initialized, then we are ready to receive the invokes for the function. So when we receive the invoke for the function, there is no specific ordering on this extension will receive first versus the second extension will receive the next. All the invokes are directly passed to all the extensions. So when you invoke a function, the platform and the runtime sends a message to the OpenTelemetry extension that, hey, I have initialized, do what you want to do in terms of initialization. And that's where we do the dependencies we bring in all the dependencies of OpenTelemetry. We initialize the auto instrumentation for Python and so on. And then once the initialization is done, once the invoke has been received, extension again responds back to the platform saying that, hey, I have finished my invocation and here is my response. And then the final stage is the shutdown phase, right? So when the invoke has been completed, when the function invoke has been completed, we want to go and very subtly shut down the extension. So shut down the OpenTelemetry collector. The reason why is OpenTelemetry collector might buffer the data for a certain period of time, and I'll go deep into that, how it's buffering the data and so on. Or the OpenTelemetry SDK is buffering the data and sending it to the OpenTelemetry collector, actually, in this case. So the OpenTelemetry we can signal the OpenTelemetry collector to push the data out to the backend services so that we don't lose any of the observability data that has been collected and stored. So again, the runtime is shut down before the extensions, and once the extensions are ready, the extension are shut down, they have to give a signal that the shutdown is complete. For some reason where the extensions cannot be shut down, a kill signal can be sent. Okay, so now let's go specific into how a user function within the Lambda runtime works with the Lambda extension for the OpenTelemetry collector, right? So what we have done is, if you look on the left-hand side, we have this user function, which is kind of the execution flow. The OpenTelemetry SDK and the OpenTelemetry collector is, the collector is part of the Lambda extension. We create one layer that bundles the OpenTelemetry SDK and the collector into one executable. I'll show that in the demo, and that works in conjunction with your Lambda execution. So for example, let's say an invoke came in, your user function is now invoked, it's executing. Telemetry data is being collected and it's sent to the OpenTelemetry SDK. So we have the OpenTelemetry SDK as well as the collector. The SDK has bundled the APIs and all the components that Ted mentioned in a few slides before. And the SDK then batches the data for 5 seconds. So you can have within an invoke, you are processing multiple executions, right? So let's say there is a for loop, or you're calling an S3, and then you're calling an API, you're validating authentication, and then you're calling DynamoDB and so on. So all that instrumentation data is collected and batched for 5 seconds. Once those 5 seconds are done, automatically we have a timeout flush that then calls the OpenTelemetry, sends the data to the OpenTelemetry receiver within the collector, and the collector then sends it to the receiver, then sends it to the exporter. The exporter flushes the data out to the backend service. So it's like close to real time happening into where you want to send the data to. What happens when the function invoke ends, right? So you have stopped invoking the function. What we do is we do a force flush. There might be some telemetry data that has not been sent out because the 5 second timeout has not been reached. So we do a force flush and we signal the Lambda extension, which has the collector, saying that, hey, we are ready to send the data out. We send the data out directly, and which then calls the monitoring backend, flushes the data to the monitoring backend, and then sends the response. So this force flush is a synchronous process to ensure that all the data that has been buffered, that has not been flushed out because the timeout might not have been reached, is then flushed out to the monitoring backend so that we don't lose the data. Okay, so what's coming next, right? So again, with AWS distribution, the Lambda support is only for Python today. We are actively working on 4 other languages and more in future, so Node, Java, Go, and .NET. We also want to emphasize that that the instrumentation is very easy and simple to do. So we try to do auto instrumentation capabilities in language specific SDKs. We cannot do it in all the languages, for example, the scripting languages. So we focus on Java and .NET. We are also going to provide a managed layer, an AWS managed layer. So it becomes, instead of you creating your own layer, you just have to search for the managed layer, add it into your function through CFN or SAM templates or the console, and everything would be set up for you, ready to go. Also, we are going to add more vendor-specific exporters. So today we support X-ray and we support OTLP exporters. We are going to support other vendor-specific exporters to send data to other partner solutions that you would like. Batching of the data today is only within an invoke. We want to batch the data across invokes. So if you have a high-scale execution or high-usage application, you can batch the data across invokes to have so that you don't reach the throttling limits of your backend monitoring services, and all the data is then sent in within an acceptable network traffic range. We also are focusing on logging support in OpenTelemetry as well. Once the logging specification is defined and executed on, we'll add it into the AWS distro for OpenTelemetry. And then in the end, as the logging is defined, we'll have better correlation between logs, metrics, and traces. So now let's go to the demo. Let me start with like a small demo that I have, and then we can take it from there. Let me share my screen. Again. Okay, so there are the demo that we would like to do is show kind of an API invoking Lambda function, which then invokes DynamoDB tables. We want to show kind of a semi-real use case. And with that, I want to show without OpenTelemetry what data you can collect. And then with OpenTelemetry, with just few clicks, adding a layer, what data you can collect and how easily you can send data to X-ray as well as Lightstep. So we'll try to kind of mimic that. Hopefully everything will work. Then we'll go to dive deep into how you can use X-ray to look at the traces, and as well as we would like to show how you can do the same thing with Lightstep, and Ted can talk a little bit more about the other functionalities in Lightstep on triaging and what innovations they have done. Cool. So I have this simple Lambda function. It is in Python. Written. It's just basically making simple calls to insert an item in the DynamoDB table. What I will do is I will just test this from my console a couple of times just to make sure, as well as I'm going to invoke like few calls in a loop to make sure we can kind of keep executing on it. So I have that on the side. So this does not have any OpenTelemetry as yet, right? So I have a simple Lambda function in Python making DynamoDB calls. So if I go to my console, and if I refresh the last 5 minutes, you'll see something like that, right? So Lambda function is making a call. All the calls have been successful. However, one thing you can see that I don't see the DynamoDB call that is being made, because the only thing I have done in my Lambda function is, I can get the screen. The only thing I have done in my Lambda function is I have enabled tracing for it. That's it. I have not done anything else. So I have not instrumented the code. I have not added any specific SDKs for instrumentation. However, I can, as soon as I enable it, I get some amount of code. I can look at the traces and I can look at the response time and so on. So let's walk through adding a Lambda layer into it, right? So I'm going to go to the layer section. I'm going to add a Lambda layer. I have already created a Lambda layer. We have a documentation that we can share later on how to create Lambda layer. It is on the AWS distro for OpenTelemetry developer portal. So I have this Lambda layer. I'm going to add version 5 to it. So this is where this layer has the OpenTelemetry SDK and the OpenTelemetry collector all baked into it. So you just add the layer into your function and you're good to go. In addition to that, I have to add an environment variable. So I'm going to copy the environment variable and I'm going to explain what that environment variable is. So there's one environmental variable I need to add, which is for the auto instrumentation agent. So this environment variable, what it does, it interjects the Lambda handler and it enables the auto instrumentation. So basically in auto instrumentation, what we do is as the Lambda extension is initialized, we automatically go and initialize all the OpenTelemetry libraries and make the connections so that when you invoke those libraries, automatically the instrumentation is done. So one of the examples is when you are making calls to AWS services, automatically the calls that you are making downstream will be instrumented. So what I have done is I have added the layer. I'm going to just do a couple of tests from here. I have enabled auto instrumentation agent for it. I have also added some random failure modes. So invalid product ID and so on, but I'm going to execute a couple of times. And if I go and hopefully if I refresh, you would see a DynamoDB node as well connected. So I made the calls from my API. Remember I was invoking an API, which then invokes the Lambda function. And then hopefully as the time comes in, otherwise I'll have to go a little bit back. You would see, so before adding the OpenTelemetry layer, I didn't have this DynamoDB node. But as soon as I added the OpenTelemetry layer, automatically without changing a single line of code, just adding the layer and adding the environment variable, now I'm able to instrument my AWS calls that I'm making to DynamoDB or S3. In my application, I also have some basic errors, random errors. So let's look at those errors and see if we can try to figure out why those errors are. So what I did is I selected that node. I looked I selected one of the traces and I'm focusing on the error. I want to find out why I'm seeing the error, right? And if you go very easily, you can see that the Lambda handler, there is a call, there's some issue in my Lambda function, which is an hypothetical error I'm creating, which is an invalid product ID, and I get the stack trace as well, right? So, and you can see where the call is going and so on. Also, let's look at maybe some of the successful traces, right? The traces that have worked. So maybe we can go and look at some successful traces and see how they look, right? So you can see that in these successful traces, my Lambda call is, I have a client calling my Lambda function, which is then calling my DynamoDB table. You can see automatically the Lambda handler instruments the DynamoDB calls. I have a success and everything looks good. Now, as the second step of this, one of the key features that we want to provide in AWS Distro is making it easy to send data to any destination in addition to the AWS destination. So what I'm going to do is just by adding a simple environment variable, I am going to send the data to Lightstep and I will see the data, how the data is seen in Lightstep as well. So what I'm doing is, let me add the environment variable and then I'll kind of explain what that environment variable is. So I'm going to add a environment variable that points to the collector configuration file. So each collector has a configuration file, and in that configuration file, you can define what data you want to collect and where you want to send the data to, in addition to other parameters, other specific parameters, such as the sampling rate and all that stuff. So let me do some tests over here just to make sure everything is good. Okay, and before explaining that collector file, I'm going to just invoke some of the data points so that we can send data to Lightstep. So let's look at the collector config file. So what I did in the environment variable, I'm saying that I want to bring my own collector configuration file. Okay, and I'm specifying the path of that collector configuration file, which is in my function itself. And if I look at this YAML file, what I'm doing is I'm sending data to two places, right? With just before I was sending data to X-ray, but by just adding this configuration file, now I'm sending data to X-ray as well as Lightstep. So what I'm saying is I'm sending data to X-ray and I'm using OTLP. And in the OTLP section, I'm specifying what endpoint I need to send to, which is the Lightstep, and what is my access key. And then I'm going to just make some invokes, and I'm going to go in the Lightstep console and see if I can get some data. So I have logged in into my Lightstep console. I am running a real-time query into this in my Explorer view, and I am able to see a lot of data around here. I am sure we will see some errors as well. I will run the function again. I'm going to send more data just to make sure it's there. You can look at individual responses. You can see how the Lambda function is integrating. What is the latency? What are the correlation keys that that you can get? Let me try to get more data over here. I'm trying to see if I can post an error actually. Let me try to post more errors so that we know that the data is coming. So this is real data that I'm running and it's sending. It's like real-time queries that we are making and getting the data. So let me go back 1 second, maybe.
Yeah, there you go.
Yeah, so I got some errors, right? So I'm creating these fictional errors and I'm trying to see why, make sure that that data goes, we viewed it in X-ray. I wanted to make sure we are seeing it in Lightstep as well. So I click on that error and automatically you'll see in this correlation tab, what are the events, what are the log events, what is the stack trace, what is the error message and so on. So with this, like we started, right? Like we showed very easily how you can instrument your existing application. Just add the layer of Python and in future other languages. By default, it sends the data to X-ray. If you want to send it data to any other vendor, you can add your own configuration file. It's just a very simple YAML file. And even without writing a single line of code, you can start collecting data in like few seconds or few minutes. With this, I would like to hand it over back to Ted. I know he wanted to talk a little bit more about Lightstep and its debugging capabilities. Ted, you want to take it over from here?
Yeah, absolutely. Just to reiterate, because we've just been looking at these kind of small examples, so you can see a bit about tracing and see how this works on Lambda. But I did want to go over the fact that you can, when you've got lots of data in more of a production environment, the way tracing can tie some of these tools together. So we're looking at a larger system in Lightstep right now. Here, let me get our little Zoom Chrome out of the way. So you can see, for example, there's a number of systems involved. You can see some of them have errors. And you can see a latency histogram. So these are all the different operations sorted by time. So you can see how many are in each time bucket. We've got some operations that are here all the way at the extreme. So you can focus in on this particular set of operations and say, well, I want to know information about this. And when you do that, you start getting correlations. So for example, here, the highest correlation we can see with slow requests is Kafka partition 4. And you'll notice that some of the bars turn black. So this all seems to be clustered up. So operations that are labeled with this attribute are all clustered up and being kind of slow. So that's interesting. And if you wanted to group by that Kafka partition, all of a sudden we can see the different Kafka partitions. And we notice that they're all fairly slow. Oops. This demo environment's being a little fussy for me. Apologies. Here, let me reload this. I think our demo is a little under-provisioned. So here, if you have a look, Kafka partition 4, you can see these are significantly slower than the rest of the partitions. You can also see the span count, the number of operations hitting partition 4 seem to be a lot larger than the number of operations hitting the other partitions. So that already tells you something's up, right? Like there's some kind of rebalancing that probably needs to occur. But you can then also click into this and have a look at the actual operations. And if I click into one of these things, I can look at an individual trace. So these are the trace graphs that I was showing you before. And if you're trying to figure out where the time went, this black bar represents the critical path, which is our guess for what was actually holding the system up. So if I look at that particular span, it's called wait for client queue. So it's calling a backend service. It's trying to get something from a queue, from a Kafka queue. and it's waiting. So this sort of ties together with what I just saw, that there were a large number of requests going to this particular Kafka queue. And so the latency we're seeing is because things are queued up waiting for the other requests to complete. So that's an example of something where you now know you need to go look at your Kafka system and figure out how to rebalance it. Just to give you an example of how to look. Oh, and I should mention, look how you can you have all of this information tied together. If you were trying to collect all of this information from a logging system, you'd have to do a fair amount of querying just to piece together such a large distributed trace. But looking at to just see how traces can relate to metrics, here I'm looking at a dashboard of metrics. For example, I'm going to look at this API gateway, and I'm looking at latency, rate, and error rate. So I can see there aren't any errors here. The rate of operations is somewhat steady, but there's these latency blips. So what's going on with this metric? You might have a metric in another system if you were just recording latency as a metric. But here you notice we have all of these dots, and each one of these dots represents a particular operation that contributed to this graph. So I can click out here to one of these outliers and look at a trace and start to get a sense of what was actually going on. So in this case, it looks like a Cassandra client query is taking over a second. So boom, I've already gone straight from a metric giving me an alert to a trace and a root causing the issue. So that's the kind of quick movement that you can do once you have all of this data in a single system. Okay, this is more of a OpenTelemetry demo, not a Lightstep demo. So that's all I want to show Lightstep at this time. But I just want to give the impression about like how fast you can start to move once you have all the data in one spot. All righty, and I think that's it for our presentation. Nizar, thank you so much for showing off all of the Lambda stuff. That's really exciting. Could you tell a bit again about what the roadmap is for Lambda development? Like, what other languages are you looking at? Oh, you're muted.
Sorry, our near-term roadmap is focusing on kind of the two things. One is expand on the language support. So our next language is Node.js, Java, Go, and .NET, those 4 of them. And then the second area we want to invest in is making it easy for customers to collect data, right? So invest in in auto instrumentation as well as managed layer. So customers can just search for the layer, add it, or use it as part of their CFN template or their SAM template and just start collecting instrumentation. So those are the 2 key areas in kind of the next 1 or 2 quarters we are focusing on.
Awesome, that's great. For people who are super interested in Lambda and want to actually get involved in development, I just want to mention we have a Lambda working group. It meets once a week. If you go to the OpenTelemetry community repo on GitHub, you can find the links to where all the different SIG meetings meet, including the Lambda one. So we hope you contribute, and we hope to see you there. Thank you all.
Thank you. Bye-bye.